many have finished? I asked that it be due today on Monday. Due on Friday then. Finished the coin flipping assignment. I sent out the data on Monday. That should give you everything else that you need to know in order to complete it. Yeah, Matt.
Okay, I'm just a little confused on what the assignment actually is. Is it like that paragraph on the first worksheet?
That sheet that I gave you, the worksheet of doing all the work,
Yeah.
towards the end, it asks you to create a graph that basically shows you how the estimate of the frequency of heads changes as you increase sample size. So you can take that data set that I've given you that has all of your coin flipping on there, break it up into runs of 10. And so you start with the first 10, which I think is, who's in the first run of 10? I forget who it is, but the first run of 10 there, I believe the frequency was 0.56. The second run of 10 was also 0.56. So the first run of 20 actually ends up being 0.56. The next run of 10 was 0.54 or something like that. So the first 30 trials ends up being 0.55 something or something like that. As you continue looking at successive groups of 10, you begin to see the frequency of heads changing over time as it converges towards what should be the theoretical expectation of 0.5. You can only do that so far with students flipping coins because it just becomes difficult. Then at the end I say, here's a script that basically has been written in R. Go and run the script, because what the script allows you to do is it allows you to do 1,000 coin flips, which is 100 sets of 10, which is a much bigger data set than what you guys have. And then at the end of the script, it says, now alter the script to give you even more runs. Instead of 100 runs of 10, 1,000 runs of 10, 10,000 runs of 10. And what you'll see is over time that thing just converges on the theoretical expectation of 0.5. And then just turn that in. So it should be.
So turn in like the
should be the
graphs
work
that we get from R, and then the graph that we make.
Yes.
Class.
And the graph that you make should basically have on the x-axis should be essentially the sample size, and on the y-axis should be the estimated frequency of heads. It's a really simple graph. Back before we worked in R, I had people just do it in Excel, but you can do it however way you want to do it.
Okay.
Yeah, so all I need really is the worksheet itself showing your results. Many of you, when you submitted your results to me, you actually just showed me the portion of the worksheet that you had done so far. And then at the end, I asked you for a graph showing and this should start out at 10 coin flips, 20 coin flips, 30, 40, 50, 60, 70, 80, because that's how many I got from you guys. And this is cumulative, so what is it after 10, what is it after 20, what is it after 30, what is it after 40, what is it after 50? In the spreadsheet that I sent you that has the data, I've done those calculations for you already. They're in a separate table. But then on R, you're able to do 100, you're able to do 1,000, you're able to do 10,000. You could do 1,000,000 if you wanted to on R. It takes R about a second to do it, but that's overkill. By the time you get out to this area here, you're already at what is essentially 0.5, which is what you would expect. And you don't start very far from 0.5 at the beginning in reality. This once again gets the point across that it doesn't take very many samples to get pretty close to the right answer. To get to the exact right answer, it takes a lot more, but do you really need to be at the exact right answer? You don't, you just need to be close enough in many ways. So that's all it is. that's why it's also not a very high point count in terms of contributing to your total grade. So you've done most of it at this point. Friday, we are about 2 days behind, but Friday we will definitely get to distributional tests. So in the schedule, when we get to distributional tests, it gives you readings from chapter 14 of the Quinn and Keogh book on statistics. So definitely go and read those sections that are in the daily schedule, because we'll start talking about distributional tests on Friday, because I will have finally finished beating sampling theory into your heads, which are probably sick of by now. So, other questions?
Are we supposed to submit our assignment in Moodle?
No, just hand it in. Yeah,
Okay.
just turn it in. Other questions? All right. We're nearing the end of building the ideas that undergird our ability to do the things that we want to do. Last time we were talking about this small sample on body temperature, trying to get across to you what a 95% confidence interval is. Generally, this is how most people teach 95% confidence intervals. They generally teach it as a way of getting a handle on what the population mean is. I tried to drive the point home to you last time that I think a more productive way of thinking about the confidence interval is relating it to the distribution of sample means. So if you look at this confidence interval, which we calculated last time, a better way of thinking about it is to say if you sampled this population 1,000 times, you should expect 950 of the means to fall within this range. You should expect 50 of the means to fall outside of that range. So the confidence interval is related back to the distribution of sample means. The reason that this is nice is because if you take another sample of similar size from the same population, there's a 95% chance that it will fall within that range. So if one of your goals is to tell if sample mean A is different from sample mean B, this is the most productive way to think about confidence intervals. What's the probability that these two means came from the same distribution versus came from two different distributions? And that's oftentimes what we're trying to figure out. But in order for this confidence interval to be valid, you have to meet certain assumptions. The samples that you've taken are random, the observations are independent, you've recorded your data accurately. By the way, the term accurate is one of the terms that students at Williamsville College and probably everywhere misuse most often. What do we mean when we refer to the term accuracy?
True value.
So accuracy is the degree to which the measurement that you have made reflects the true value of whatever that thing is that you've just measured. Are you guys familiar with the National Institutes of Standard and Technology? Anybody? Maddie, did you just nod your head? Did you just nod your head? What is the National Institutes of Standard and Technology? If you don't know, you all have computers sitting in front of you. Go find out. What is an IST?
out of the Department of Commerce, and they promote U.S. innovation and industrial competitiveness by advancing measurement science, standards, and technology.
Yeah, so they're the people who govern measurements. And so, and for whatever reason, this isn't popping up on my own screen. That's odd. Okay, weird. Somebody hasn't hijacked my screen, have they? So, if you guys wanted to know what a meter is, so I just looked up the International Standard Meter. And if you wanted to know what the meter was, there was a time when you would go to France, and in a bolt, in a box, lined in velvet, there was a bar, and this bar was a meter long. And I'm trying to find a photo of it. Ah. It looks like this. It's made out of a particular type of metal that doesn't change lengths when it warms up and cools down, and it is exactly a meter long. And forever, that was the International Standard Meter. It was held in France at basically the French equivalent of our National Institute of Standards and Technology. And if you wanted to know what a meter was, you could go to that meter, and that meter is the meter that is the national standard, the international standard rather, for how long a meter is. One of the things that you will notice about this bar is, what does it not have on it that your meter stick had on it the other day?
Centimeter marks.
Doesn't have centimeter marks, it doesn't have millimeter marks. It's just a bar of metal that is a meter long. So when we talk about accuracy, the question is, how much does our meter stick that we pick up at Lowe's or Home Depot or whatever, get out of the biology stockroom, how well does that meter stick reflect the actual standard meter? The degree to which it doesn't is the degree to which our measuring instrument is inaccurate. Nowadays, rather than comparing it to a bar, we've agreed upon a measure of meter that is based on a particular wavelength of light. And so that's a different standard, and these bars are not valid anymore. At the National Institute of Standard and Technology in the United States, which is, I think, is it in Colorado Springs? Is that where it said it was? Anyway, it doesn't matter where it is. It's in Colorado somewhere. They also have a bar that is the national standard bar that is based on the bar that is in Paris. But once again, this term accuracy, when we talk about assumptions, is based on how well our measurements reflect the actual value that we are trying to measure. You make sure that your data are accurate by making sure that your instruments are calibrated correctly. Whenever I go into the field with my students and they have to take a meter stick because they need to measure something, I tell them to don't use the meter stick as a walking stick, because when you use the meter stick as a walking stick, it wears down one of the ends, and as a result, that meter stick is no longer a meter long. It's a little less than a meter long, and if they have to measure anything more than a meter, their measurements are going to be inaccurate because they have an improperly calibrated meter stick, because they've been using it as a walking stick rather than a measuring device. But stick a stick in a person's hand and they're going to use it as a walking stick. So we sometimes take them out with tape measures, but one of the things about tape measures is that they stretch, even though they're made of fabric that is woven in such a way to remove stretch. It does have a little bit of stretchiness to it. That can make your measurements inaccurate. In order to combat that, foresters, you will oftentimes see them using metal tape measures because metal tape measures are less prone to stretch. And so all sorts of ways in which you can ensure that your measurements are accurate. So assumptions: the sample is random, the observations are independent, the data are accurate, and the distribution of the sample statistic of the population from which the sample is drawn is normally distributed. Notice how I'm not saying the original population is normally distributed. I'm saying that the sampling distribution of that population is normally distributed, because that's almost always the thing that matters, because from any given sample we calculate some summary statistic. It's that summary statistic that needs to be normally distributed.
Now, in the previous session, we did the mean.
So in almost all cases, this is the distribution of sample means is the
Okay.
thing that we're talking about. But it could be any statistic, any summary statistic that you pay attention to. So if you went and took a sample from a population and you wanted to look at the median, you could test to see if medians were different. And as long as those medians, that distribution of medians from the population has a normal distribution, once again, it would be satisfied. It doesn't have to be the mean, it just has to be whatever your statistic is.
So the batch of data we had last time, the mean was normally distributed, so we could know the same batch of data, the median, because the
Oh,
mean
because-
was
so-
normal. The median will be normal too. I mean, if
Yeah.
one of them, if you test one,
Oh, no,
and
not
that's
this.
normal, then all the other statistics will be normal.
One of the nice things about a normal population is that for the population, the mean, the median, and the mode are all the same. Such that if you take a distribution of sample means from this population, it's going to be narrower. So if this is the population, this is the distribution of sample means. It will be normally distributed because the original population is normally distributed, but it will also be normally distributed because of the central limit theorem. Same thing applies to median, same thing applies to the mode. But seldom do we test medians and modes, at least in parametric statistics. On the other hand, if you have a bimodal distribution, the mean is here, but this has two modes. So the modes are going to be different. And so mode does not adhere to this in the same way that mean does. Median will still be the same because it'll be 50% of the data are above that mean, 50% of the data are below that mean. On the other hand, with skewed data, once again, the mean is going to be over here someplace because these high values skew the mean. That's why we refer to this as skew. The mode is here. The median is somewhere around in here. So if we were to take this original population, create a distribution of sample means, it would have, let me draw this better. It would have a distribution of sample means that was normally distributed because of the central limit theorem. It would I've never thought about this in terms of mode and median. I'm assuming that the mode and median would also be normally distributed because for any given sample, the sample median and the sample mode are going to fluctuate around. And once again, they would fluctuate around those measures of central tendency, and they would fluctuate around in a normal way if, once again, your sample sizes were large enough. So that's why I've written this generally, it's the sample statistic that matters, whether it's mean, median, mode, whatever. We could actually take the central limit theorem script that I wrote that is on the Moodle site, and we could rewrite it to calculate mean and median and mode, and we could actually test to see if that's true. Maybe I'll do that between now and Friday. Your textbook, one of the reasons that I chose your textbook is that it has worked examples in the textbook, and it provides the original data for all of those worked examples. In chapter 2, it is where they're talking about measures of central tendency, these distributions and sampling theory ideas. There is a data set there. It's box 2-3, I think. And in this data set, it's basically stream data from, I think, somewhere in New Zealand. And the stream data basically have to do with the sulfur content of the stream, the chloride ion concentrations of the stream as these streams vary in elevation. And one of the exercises that they do in the book is they just are talking about the mean and constructing confidence intervals, et cetera, et cetera. If you look at the chloride ion concentration, the chloride ion concentration is 22, and you can calculate what the confidence intervals are for this. What I've done in R, if my computer will cooperate with me finally, I've come over here to R, and I basically got the chloride ion in a script. So the first thing that you do, the first thing that I always have you do when you get into R is I have you check what working directory you're in. And so that's what getWD is. GetWD basically says get working directory. In R, the first mistake that students make is they open R directly from R, and as a result, it's opened in whatever directory you've stored your R stuff in on your computer. And usually that's the applications folder, and so you're operating out of applications. I am operating out of my computer's segment of my hard drive, the 2020 DTS218 folder, a folder called RScripts. You guys are mostly data science people, so I'm assuming that you know about the internal structure of your computer. You can get access to your entire hard drive. So I'm working in a Mac environment, but the same is true, but actually more difficult to access on a Windows machine. You have to go through a couple of special steps to access this on your Windows machine. But within this, I could set up a variety of different users. On my computer, there are only 2 users, the administrator, which is the people in IT, and myself. In my user folder, I have all of my folders that are all on my computer. Back in the old days, we referred to these folders as directories, and I have a directory on here that is devoted to this course, and within that folder, I have a folder where there are RScripts. If you just open up R straight away, let's actually just do this. I'm going to close R on my computer. If I just go to the R icon that I have down in my toolbar here and open it up, when I go down here to get working directory, it just tells me that I'm in my user account. I'm not in my applied statistics folder. I'm not in RScript within that folder. When I then go down to load the data, you're going to see that I get a red error message down here, and it says cannot open the connection. Cannot open the connection is a weird error message, but what it's basically doing is it's R's way of saying you sent me to look for something, and when I got there, I didn't find it. And the reason I didn't find it is because the data file that I'm asking for here, which is a data set by Lovett, Lovett is the author who originally published these data. I sent it looking for lovett.csv, a comma separated values file, and it couldn't find it in the user Plowinski space. Because I haven't told it that it's not in the user Plowinski space. It's in the user Plowinski 2020 DTS 218 rscripts directory. And so I can go and fix this by setting directory. But for this, I have to change this because this is from the previous semester. I can say it's in the 2020 DTS 218 folder, rscripts. Let's see if that gets us anything. And now set WD means set working directory. I want to set the working directory to be not the directory where R lives, but a directory where my data live. And when I get working directory again, it has changed the directory to the directory where I know my stuff is hanging out. My data file is hanging out. And now when I go to load that data file, it loads it correctly. Did not give me an error message. So you can go through this process of clicking on the R icon, loading R from wherever R is stored, and then telling it where your data are, if you want to. Or you can do what I get in the habit of doing, which is essentially storing each of my projects in their own directory. The data for that project go in a directory, the R script for that project goes in a directory, and then rather than opening R from my toolbar or from the applications folder or wherever you have it stored on your computer, actually just open that specific R script from wherever that specific R script is. When R opens under those conditions, it's opening R from the directory that you're working in, and then you don't have to go through and set working directory. If we close R again, and I go to this class's folder, I go to my R scripts, and I open the chloride data script. When I go to get the working directory now, it tells me that I'm where I'm supposed to be. I don't now have to set working directory because I'm already in the directory that I want to be in, so that then when I scroll down here and load the data file, it loads correctly, and this is what it looks like. It's a bunch of localities that exist at different elevations. It's got sulfate, it's got chloride, it's got a new value here that I've basically done where I've essentially decided that high elevation sites are elevations 500 meters and above, and low elevation sites are below 500 meters. And so we have our data in there. We need a couple of libraries. I've separated this into high elevation and low elevation sites, and I want to see if chloride ions are different at high elevation sites and low elevation sites, so I can just run an analysis of variance, which we haven't gotten to. But one of the things that you'll notice here is that the p-value here is 0.04. It's just over the cusp of significance, so it's slightly significant data. High elevation sites are different from low elevation sites in terms of their chloride ions. Concentrations. We can make a plot of this using summary SE. I've told you about this function before. This is a function that you used to have to copy the function into every R script that you have, and now it's in this package called RMISC. Summary SE is basically going to calculate summary statistics on the data file that it's going to use the measured variable chloride, and it's using the group variables elevation.f, and it's going to store it in a new data frame called CI plot. When I do that, it doesn't do anything other than say, I ran that, now what do you want me to do? I then have to call CI plot up to see what it is. And so what it's basically done is it's telling me I have two categorical variables that I put in the data file: high elevation, low elevation. There are 22 observations in the high elevation, 17 observations in the low elevation. The mean for chloride is 19.3 for high elevation, 27.4 for low elevation. This is the standard deviation, the standard error, and the confidence interval. So you can calculate all these things by hand, or you can just tell R to do it yourself using the summary SE. Summary SE basically stands for summary standard error. You need the standard error of the mean in order to calculate what the confidence interval is. You could do all of this by hand. You could look up what the t-statistic is for an alpha level of 0.05 and 16 degrees of freedom and 21 degrees of freedom, and do the calculations yourself, but this will do the calculations for you. Yeah.
So the CI number, well, that's the width of the confidence
That's the
interval?
width of the confidence interval.
Or that's,
So confidence interval is typically the mean plus or minus the confidence interval, but this plus or minus confidence interval is the t-statistic at an alpha of 0.05 and the number of degrees of freedom multiplied times the standard error of the mean. And so there's a certain distance above the mean and a certain distance below the mean. That confidence interval is this part that I gave you last time.
okay, so I'm confused between what's a confidence interval and what is half of a confidence interval. If I'm gonna do a plus and a minus, one of them is half.
Yes, so the confidence interval, so this is the width of the confidence interval above and below the mean.
It's
That width of
one
that-
side.
It's one side of the confidence interval, yes.
So it's half. I mean,
Yes.
value-wise, it's half the confidence interval.
Yeah, so
If somebody wants to say, how wide is that target? That target is 3.6.
3.6, yep. Typically, the way you see confidence intervals written is so the mean lies between the mean minus that and the mean plus that. And so when you see a confidence interval, what they're basically giving you is this piece of this. To tell you how far do I go above the sample mean, how far do I go below the sample mean to encompass the 95% confidence interval. So the confidence interval actually is this whole thing. It's the mean plus the confidence interval and the mean minus the confidence interval. That's what it is. You can then use this to plot a plot of the data, and this is actually what I'm getting to. ggplot is a package within R. It's probably the easiest, most flexible way of plotting things. And so whenever you're making a plot, you want to have loaded the package ggplot, which we did up at the beginning. But then there's a bunch of things that you can do, and you don't have to do these things. You can do them. There's some minimum things that you have to do to get a plot. And then there are other things that you can do to make your plot nice. So I'm gonna just do this so that we can see everything. So basically, just to decompose this thing for you, I'm calling up ggplot. I'm telling ggplot to make a graph of the data that is in the data frame CI plot, which we just made. The aesthetic statement basically tells ggplot what you want to do with the data that are in that data frame. And so I wanted to find the x value as elevation and the y value as chloride ion concentration. I want to put an error bar around those data. The error bar is, and it will have a minimum value of the chloride ion concentration minus the confidence interval, and the chloride ion concentration plus the confidence interval, and I'm gonna put a cap on that bar that's 0.1 units wide. I'm going to want it to demonstrate that as a line. I'm going to want you to plot a point where the mean is. The point is gonna be size 5. It's a shape that is basically a circle with a border on it. The fill of this I want to be white. The X label on the graph is going to be elevation. The Y label is going to be chloride ion concentration. This is going to have a title called chloride ion concentration by elevation. I want it to be a black and white plot rather than some weird colored plot. Scale X discrete basically tells me that I want you to give my X axis discrete labels, and I want those labels to be high and low. Then this is all a bunch of formatting. It's basically saying, what size do I want the plot title to be? I want it justified so that it's centered over the plot. I want the X title Y to be a certain size, the X title, the axis title for X to be a certain size, the axis text to be a certain size for both X and Y. So this is just what I refer to as a formatting block, telling me how things will look. When I run this, it's going to basically take the data that are here in CI plot, high and low. It's going to report the mean, and it's going to report error bars that are based on the confidence interval that it is calculated. And it's going to look like this. Now, what are problems with this figure? From the standpoint of making a determination as to whether or not these two means are different from one another. Yeah, Athos.
I think we can use the term polarized. You're high, either high or low. There's no kind of like a mid-term.
Well, but that's just the way I divided up the data. I just made an arbitrary decision. High is above 500 meters, low is below 500 meters, and then looked at chloride ion concentrations to see if elevation had an effect on chloride concentrations. And in this case, it says that they do, but what's weird about these data?
The plot's not good for it, I guess.
The plot's fine, the plot is reflecting exactly what the data are.
What's weird about it is the question?
Well, yeah, so we've calculated 95% confidence intervals. What do those 95% confidence intervals look like?
Well, yeah, but like one's big, one's small, you would think.
One's big and one's small. And so one of the assumptions of any statistical test that you do is that these distributions of the sample statistic are normal. But when you're comparing means, there is another assumption that you need to make. Variances are similar. And here is a case where variances are not similar. One part of the data are much more variable than the other part of the data. Remember, what does the confidence interval tell you? The confidence interval tells you if I go to this population and grab another sample mean out of the population, I would expect 95% of those new sample means to fall within this 95% confidence interval. So a mistake that students come to statistics in college with is how to interpret error bars. And oftentimes, they think that two means are not different if their 95% confidence intervals overlap with one another. That is not what a confidence interval says. A confidence interval isn't about overlap of confidence intervals. Confidence intervals are about inclusion of the mean. A 95% confidence interval says, if I go to that same population, draw another sample of the same size out of it, 95% of the new sample means that I draw out of that population will fit within this confidence interval. So when you're looking at a figure, you should be asking yourself, does this mean do what relative to this confidence interval?
Doesn't
Fall
fluctuate.
within it.
Does this mean fall within this confidence interval? If it does, we could have just as easily gotten this mean from this population because of its confidence interval, as we could have gotten that mean, in which case we would say that those two means are not different. They were drawn from the same underlying population. Here's the problem when you have unequal variances. Could this mean have come from the population that generated this confidence interval? Yes. Could this mean have come from the population that generated this confidence interval? No. Okay, did these two means come from the same population or from two different populations?
Second pollution.
You have as much evidence for that as you have for what you said, which is the different influence. Why? Because if you ask, could this mean have come from the population that generated this confidence interval? The answer is yes. Could this mean have come from the population that generated this confidence interval? The answer is no. When you're faced with a yes answer and a no answer, what is the actual real answer?
Both.
No, the answer is you have no way of knowing.
Well, awesome.
Which is why this is way more important than this is.
In fact, that first one's almost always gonna be true, right?
If you invoke the central limit theorem, if you have sample sizes that are big enough, you can invoke the central limit theorem and say, central limit theorem, bitch, I did that. A sample size of 35, I'm covered on the normality front. This will bite you in the butt every time. Which is why statistics textbooks are so infuriating. When they list the assumptions, they talk about random samples, they talk about independent samples, and the next thing that they talk about is normality. The fourth assumption is always homogeneity of variances. Are the variances of your two samples similar or not? And that's the one that if you violate it, you're dead in the water. Because even though the statistical test that we ran, which is just comparing the high elevation to the low elevation means, even though that's told us that these two samples are different, that test assumes that this is true. And this is decidedly not true.
Okay,
In this case.
semantics. We
Yes.
really started with one sample, and we went out in one day and we gathered one big batch of data, right? Or
We
something
did,
like that.
but-
And then.
But I, as a researcher, am interested in the effect of elevation,
So
and
when you split it into the categories based on elevation, now we can say these are two samples.
I want to know, is the population of chloride ion concentrations in high elevation streams different from the concentration of chloride ion in a population of low
Okay,
elevation
so,
streams?
so once you made that category split, we
Yep.
have two samples or we have two populations?
Well, we're asking, could these samples have come from two different populations, a high elevation population, a low elevation population? Or are those two populations actually just different divisions of a bigger population that is all streams on a mountain?
Okay.
We know that as water percolates down through ecosystems, it picks up all sorts of dissolved substances, sulfate, phosphate, nitrate, chloride, all these things tend to accumulate the further down in a watershed you get. And so we have expectations that concentrations of nutrients will be lower at high elevations than low elevations. And so a common way in which we divide stream chemistry is based on elevation if you are looking at streams that have an elevational component to them.
So we're gonna look at these two samples and see if they are so statistically different.
That you can
they
treat-
lead us to think
think that
two different populations.
There is a population of high elevation streams and there is a population of low elevation streams. We sampled these populations and they are actually different populations.
Okay.
We're basing that decision on the sample means that we calculated that we presumably drew from those two populations. But the problem within making that decision is that the low elevation populations are, the low elevation samples are very variable, and the high elevation population is less variable. And then that makes our decision as to saying they're different or not more confusing, because if we think of it in a confidence interval sort of context, we could have drawn this sample from this underlying population, but we could not have drawn this sample from this underlying population. So if that's the case, what's the right answer? Which is why variance is the more important of these two things. We can rely on the confidence, on the central limit theorem to tell us that this is going to be true. We cannot rely on the central limit theorem to say that this is true. And I've never written the word CL bitch on
Yeah, you might wanna clean that up a little bit.
the board before. So let's graph this slightly differently. Because one of the problems with showing data this way is it tells us what the mean is, it tells us what the confidence interval is, but it doesn't give us any insight into what the data are. Well, we could actually just get rid of that, and we could make it give us the points. And when we do this, what we would see is that the two populations are actually very similar, except that the low elevation data have some skew. 1, 2, 3 data points. These 3 data points pull up the mean. They drag that mean up, pulling the overall result towards saying that these two things are different. But what you really have is you have a bunch of data that are very similar with 3 outliers. Now, there's a lot of density of points here. We can show this another way where we jitter the data. We basically just tell R to randomly move the data off to the side so that you can see all of the data. And once again, we see a similar picture. A ton of data all clustered down here, a ton of data all clustered down here. My guess is if you look at these data from here down, these are normally distributed, these are normally distributed. What's throwing this whole thing off is that point, that point, that point. Now you can see the data, you can see what the source of that wide variation is, and you can see that the conclusion that we made about high and low elevation streams being different is probably, when we did an ANOVA on this, we saw that the two sites, high and low elevation streams, were slightly different. Now we would probably conclude what?
Are the same.
They're the same, and they're just a couple of outliers, and they're throwing that off. So we would have made a type 1 error. We would have said that 2 means are different when in actuality they're probably the same. And the reason we made that type 1 error is because one of the assumptions of our statistical test was violated. And as a result of that, it made us make a type 1 error. Type 1 error concluding, in this case, that 2 means are different when they actually are not. And as scientists, as statisticians, we generally want to avoid making type 1 errors, which is why it's important to not just pay attention to means and confidence intervals, but it's also important to graph your data in ways that allow you to get access to the data themselves. Because immediately when you graph it this way, the first thing you notice is something's wonky. What is up with those 3 points? We would go and we would try to identify those 3 points and see, was our instrument not calibrated correctly the day that we took those 3 points? Are those 3 points influenced by the fact that at lower elevations there's a town and effluent from the town is now influencing those 3 points such that they have higher chloride ion concentrations than all of the other samples? We could investigate those 3 points to see if those points reflect reality or there's something strange and odd and unusual about those points that might explain why those values are so high. If they're so high because these data were taken in winter, those data points are all urban sites in these low elevation streams, and there was a lot of salt on the roads because there was a snowstorm, during the time period when we gathered these data, then that's why those chloride ion concentrations are so high. In which case, if all the rest of these low elevation sites are rural sites that didn't have that complication, you would definitely say we reached the wrong conclusion about high elevation streams being different from low elevation streams. This is the nature of type 1 error, concluding that two things are different, two means are different when they actually probably are not. Your tendency is going to be to throw numbers into R, run a statistical test, get an answer from R, and then take that answer at face value. I would encourage you to not do that. I would encourage you to take the output that R gives you, interrogate that output, look at the data that underlie that output, and then after that, decide how much stock you're going to put in the conclusion that is dictated by the statistical test. In many cases, this statistical test is telling you exactly what is true. But in some cases, the statistical test will give you the wrong answer, and you've committed a type 1 error. Or you might commit a type 2 error. So, type 1 error, and we'll define it in terms of means for the moment, is this is it for means, concluding that two means are different when they're not. We could also do this for distributions. We're about to start, on Friday, we'll start talking about how to test whether distributions are different or not. We could also conclude that two distributions are different. There will come a point when we get to regression analysis, and what a regression does is it tests to see if a slope is different from 0, and in this case we conclude we would conclude that the slope is different from 0 when it is not. These are all examples of type 1 error. Making a decision that things are different from whatever when they're not. Two means are different, two distributions have different shapes and they don't, or a regression is different from a slope of a specified value when it is not. These are all type 1 errors. And the reason that we talk a lot about type 1 errors is that generally we're looking to see if an effect occurred. If we did something and it had an effect. Education. Sometimes we deliver the same course to different sections, but we deliver that material different ways. And then we look at comparisons of pre-test to post-test scores to see if the method of instruction actually had an effect on student learning. All sorts of things that this would fall under. What we want to make sure is that as we are doing our statistics on our data, is that when there is an effect there, that we're pretty sure that there is an effect there. And so alpha is the type 1 error rate. This tells us how often we want to make those mistakes. And so kind of the standard value is a value of 0.05. We only want to make type 1 errors 5% of the time. There's another type of error though. What's the other type of error?
Type 2.
What's a type 2 error, Maddie?
When you say that two things are the same but they're not.
now change this to type 2 error.
What was this word?
I've now changed all those statements from type 1 errors to type 2 errors. It's the act of saying that two things are not different when in actuality they are.
What was the word after R?
Are not.
Are not.
But now they're not different, they are different. So concluding that two means are not different when they actually are. It's just the opposite of a type 1 error. Concluding that two distributions are different when they are not is a type 1 error. Concluding that two distributions are not different when they actually are is a type 2 error. So type 1 error and type 2 error are two sides of a coin. Type 1 error and type 2 error are two sides of a coin. Let's imagine that you are an ecosystem ecologist. You are interested in what the effect of hurricane disturbance is on forest dynamics. And so you can either sit around and wait for a hurricane to come around, or you can do something more manipulative. The problem with hurricanes is when you have a hurricane, you have a bunch of trees that have canopies, and during a hurricane, two things happen simultaneously. The hurricane comes along and it blows this canopy off of the tree, and this canopy is now deposited on the forest floor. Two consequences of that is that all of the nutrients that are in all these green leaves, and there are a lot of nutrients in green leaves, are now down on the forest floor rotting and decomposing. All those nutrients, as they rot and decompose, are going into the soil. That affects the microbes that live in the soil, the fungi that live in the soil. It starts feeding the forest at the soil level in a way that wasn't happening when all this living biomass was up in the canopy. But the other thing that happens at the same moment is that there's no longer a canopy there, and so when the sun comes out after the hurricane, this forest floor is being bombarded by solar radiation. That solar radiation makes the forest floor warmer, makes it drier. When it rains, it makes it wetter because the rain isn't being intercepted by the canopy. When it's not raining, the sunlight is beating down on the forest floor, making that forest floor drier. So the forest floor is drying out and getting wet, and drying out and getting wet. It's generally warmer. Because you've lost the canopy, you now have a bunch of nutrients that have been input to the forest floor, and you've also changed the climate of the forest floor. And so, while all those nutrients could be used by things like fungi that would feed on that dead, rotting vegetation, those fungi get killed when the sun beats down on them and makes the environment too dry, because fungi like nice, moist environments. All of these things can affect how this forest grows back. So you get this bright idea, since we don't want to wait 20 years for the next hurricane to come around, let's just actually induce a hurricane on the forest and see what happens. But one of the problems with all the studies that we've done on hurricanes in the past is that you can never decouple these two major factors, opening the canopy versus adding all these nutrients to the forest floor. So you get the bright, crazy idea, I'm gonna set up 4 plots in the forest. One plot I'm gonna leave alone and do nothing to it except sample it the same way that I sample all the other plots. In one set, I'm going to hire some arborists I'm going to cut out the canopy using arborists, and I'm going to cut out the canopy and I'm going to drop it to the ground, which is exactly what happens in a hurricane. Canopy leaves the canopy, ends up on the ground. More nutrients come in, but also you get this climatic change. But then to decouple these two things, I'm going to go to one set of plots. I'm going to cut the canopy out, and I'm going to remove it. And then the canopy that I take out of this plot, I'm going to cart over to another plot, and I'm gonna drop it in a place where I have not cut the canopy, but I've added all of this detritus. Because now I can look at the effect of climatic changes without the nutrient additions, and I can look at the nutrient additions without the changed climate. Now I'm gonna do these on 20-meter plots, 20 by 20 meter plots. But because of the forest, this is in a tropical forest in Puerto Rico where I work, but because the forest is very tall, we actually made these plots 30 by 30 meters so that sun can get down to the measured plot. And so we have these 5-meter buffers on either side. So it's actually 30 by 30 meter plots. Do you know how much canopy is in a 30 by 30 meter plot? I
How much
do.
what?
How much that canopy weighs? I do. You know why? Because we weighed it as it came down as the arborist cut the forest down. This is not theoretical. This is something that I actually participated in. Any guesses on how much the forest weighs? It averages out to 66,000 kilograms. 66,000 kilograms. Kilogram is 2.2 pounds. Do the math. It's heavy. How long did it take us to do this?
4 weeks.
How much money did it take us to do this?
Couple weeks.
Guess what our sample size was? Sample size of 3. We had 12 plots. We had 3 controls, 3 cut and drops, 3 cut and removes, and 3 uncut with litter additions. You know why we had 3? 3 is the minimum number that you need to analyze this design. And quite frankly, we didn't want to be out there for another 6 months and another $150,000. We spent months discussing with one another. This is a large team that is doing this on a big grant that we had in Puerto Rico. And we spent months discussing what our sample size should be, trying to balance what the effect size is that we think we're going to observe compared to how much money and time we're willing to spend to get this thing off the ground. It took us 18 months to put it into place, and we have been measuring it for 14 years now. So this is a long-term project, so we're getting a lot of bang for our buck. We've already published a bunch of papers, 30 or 40 papers out of this one experiment. So it was money well invested, but we did it with the minimum sample size that we could because it was so expensive and time-consuming to do. We had to ask ourselves what's the size, what's the magnitude of the difference between these different plots that we're looking for, and can we get away with a sample size that small and still detect these differences? Now, if you're doing something like this, is anybody gonna die if you make the wrong decision? No. You'll just reach an incorrect conclusion about forest regeneration or about the effect of climate and nutrients on frog population dynamics or something like that, which is what I study. So, do you want type 1 error rates to be this stringent? What you might say is we only have a sample size of 3 because this is so expensive. So rather than this, we'll make our type 1 error rate 0.1. What that means is we will occasionally say that this experiment had an effect when it didn't. But what we'll do in the process of that is when it does have an effect, we're more likely to conclude that it did have an effect. Now imagine that you are a cancer researcher. You work on glioblastoma. Glioblastoma is this hideous brain disease. Basically, when you get diagnosed with glioblastoma, 6 months later, chances are you're dead. It's bad. The Duke colloquium is coming up here in the spring. David Duke was a professor in the philosophy department here. He died when he was diagnosed with glioblastoma. He was here for the first 6 months that I was here, and after that he died, and that was the end of David Duke. Glioblastoma is hideous. You are a researcher and you think that you have a cure for glioblastoma. The unfortunate thing about glioblastoma is because it's such an aggressive cancer, you need to have a very strong chemotherapeutic agent that will get rid of it, that will eradicate it. But because it's such a strong chemosynthetic agent, in the process of taking it, you also then have a liver that is cooked. And so you're now cancer-free, but you really kind of need a liver transplant. If you are doing an experiment, if you get to the phase of doing human trials where you get to give this drug to patients, how sure do you want to be that it actually gets rid of the cancer? Given that if you're cancer-free, you need a liver transplant.
Very
Extremely certain. You want to be extremely certain. So is an alpha level of 0.05 going to be sufficient for you? Probably not. What would you want it to be? You would want a 0.01 or maybe 0.001. So liver transplant is no small thing. So you want to know that that thing really does what you say it does, because the add-on consequences of you doing that to yourself are significant. Now, in the process of doing this, you've made the criterion for making a decision that it works much more difficult to achieve. So while you'll be very sure that it works when it does, there are going to be cures that you'll look at that you say don't work when they actually do. Because you've made the criterion for saying that they work very, very hard to achieve. As you run away from type 1 error, you run headlong into the waiting arms of type 2 error. The more you try to avoid saying things are different when they're actually not, the more you risk saying things are not different when they actually are. There is nothing magical about an alpha level of 0.05. You set that as a researcher, you set that as a statistician before the work ever gets done. You say what level of type 1 error you're willing to put up with. As you lower type 1 error, make that rate lower and lower and lower, you risk not seeing differences that actually exist. You relax type 1 error, you make the wrong conclusion that things are different when they're not, but you catch the conclusion that they are different when they really are. And so these two, when I say these two things are two sides of the same coin, you have to realize that as you avoid one, you increase your chances of the other. As you increase one, you decrease the chances of the other. Type 1 and type 1 and type 2 error are important basic concepts because, one, they're related to one another. The other thing is, people think about this one a lot, and they hardly ever think about type 2 error. As a well-trained statistician, you should be able to think about type 2 error just as easily as you think about type 1 error. Yeah.
So for your case, was interesting to have a lower alpha? Why?
We didn't, because we only had a sample size of 3, which means that it's going to be harder to detect differences. The differences that we're trying to detect are really just of kind of interest to ecologists. Nobody's going to die as a result of it. As it turned out, the effect was so gargantuan that we didn't have to relax our alpha level at all. Like, the plots were like night and day. And so we made the right decision of going with the sample size of 3 because we were able to show it with the sample size of 3.
The big differences of them, right?
They were huge.
Okay.
Because we removed 66,000 kilograms of forest.
That's
and
a lot of stuff, yeah.
That's a lot of stuff. Yeah.
Just a small question, can you call type 2 error beta?
Yes, so type 1 error is represented by alpha, type 2 error is beta. Yep, that's the short answer.
Is there a rate for type 2 there?
Yeah, beta is the rate, is the type 2 error. test on Friday. And I will see you then.
And we need to,
And finish your coin flipping.
Coin flip.
That's not good.
Are you coming for the?
Email that to you, or do you prefer it on paper?
For the rest of it, you don't have to work on it together. The coin flipping part is the only part that you need to work as a team on. All the rest of it, you can
May
do.
we need like 1 or 2 questions? How many do you have left?
Can we just email that?
Yeah.
we need to vote on it separately.